Do you have any idea about what do we mean by Hall effect? In 10 plus 2, or maybe in first year, if you have studied on this, can you throw some light on the Hall effect phenomenon?
uh, it will create the potential difference between two layer. I mean, there is some distance between two layer,
Exactly.
that upper layer, lower layer, and having the formula is equal to that BVD. D is the distance between two layer, and the B is the magnetic field, and V is the potential difference.
Exactly, exactly. Yeah, yeah. So, anybody has got different answer? Okay, so if you let's proceed to the thing. If you are seeing this in my screen, so Hall effect is nothing but it's a phenomenon that's commonly used in semiconductor physics, mainly to induce some voltage. When we keep the material like this is a rectangular slab. What you see, if you look at dimension of this slab, the length of slab, if you can see here, and just to show this is the length of the slab L we have shown here. Width of the slab is shown here. You can see here, this is the width of the slab. Thickness of the slab is shown here, small t. So this gives you the dimension of this slab, the length, width, and the thickness. Okay. So this is a rectangular slab basically, and here we assume that this slab is a p-type semiconductor. Okay, there are certain assumptions we have to do before we actually explain this Hall effect phenomenon. This rectangular slab is of p-type semiconductor. That's one thing, and it has got the different faces. You can see there is a front face, what you are seeing here, and this is a these two are side faces. You can the faces has been shown with letters like D. D means it is a front face here, and B is a side face, and there is an A here, which is again another opposite face to the B, and there is a face C, which is back side, just opposite to the face D. There is again top and bottom, which we are not interested in that. Okay, so totally it has got six faces, but only we are interested in four faces, namely A, B, and C and D. Okay, this is a P-type semiconductor slab. Okay, so now there is again reference direction as shown here. This direction is helpful to you to understand the various the parameters here. Example, the current, magnetic field, and electric field. To understand this current flowing, magnetic field, and electric field, we choose this reference direction here. So reference direction, you can see that it is towards you or out of the computer. There is an x direction. Along the width of the computer, you can see there is a y direction. Okay, and the top. Okay, from vertically up above, there is a z direction. If you hold your finger, first three, either right hand or left hand, okay, the thumb will be pointing to the upside. Your middle finger will be pointing to the y direction, and x is the last forefinger, which is pointing to the x direction. Okay, so this is this is we taken as a reference direction. As I told you, this direction is going to be useful to you in understanding these parameters like current, magnetic field, and electric field. Okay. Okay, with that, let's go to the detail, the Hall effect details. Other notations, I will come back to this diagram. That is notations like Ix. Ix means it is current flowing in the x direction. There are again, we have shown here the positive reference direction like plus x, plus y, and plus z. Opposite to that, there will be a minus x. Example, you can see inside the computer there will be a minus x. Minus y is here, this way, minus y, and the bottom is going to be the minus z. So those directions are not shown here. Okay, whenever I say, suppose if there is a ey minus ey, meaning is there is electric field in negative y direction. If I say minus ix, that means current is in the negative x direction. Okay, in this direction it is flowing. If I say minus bz, that means magnetic field is negative towards ground. Okay, that's what the the thing interpretation we can do with this reference direction here. Okay, So namely you can see here the ey ex. Okay, so these are the electric fields, ey is due to the ey is the electric field acting in positive y direction. Ex is the electric field acting in along the length of the bar, okay, or towards positive x direction here. So this slab is considered to understand the Hall effect phenomenon. Okay. Now let us see who is the person behind this Hall effect. The Hall effect is was phenomenon was introduced by this person called famous person called Edwin Hall in the year 1879. Okay, so it is an important phenomenon, of course, used in electronics. You will get to know that what are the different applications of Hall effect phenomenon. What statement? What is the statement of this Hall effect? When a current carrying conductor is placed in a transverse magnetic field B, an electric field E is induced in the direction perpendicular to the current and magnetic field. I hope you understood this statement. Statement is more clear, precise, and exact. Okay. So when a current carrying conductor, that means you are placing a current carrying conductor. Already, you should have a conductor that should carry the current, and if you are placing that conductor perpendicular or transverse to the magnetic field, there should be a magnetic field in the area where you are placing the conductor. You are placing this conductor which is carrying current in the perpendicular to the magnetic field. If you do that, an electric field E get induced, and this direction of this electric field is perpendicular to both current and as well as the magnetic field. I hope so you understood the statement. Okay. So what are the advantages of this? As we said already, it is an important phenomenon in electronics, and we told about the Hall effect statement, and we also told that illustrated the diagram which is shown here explains Hall effect phenomenon. We will now watch a video so that you will understand better the Hall effect phenomenon before I proceed to the actual topic. Okay. Let me, you can all of you can watch this video for about 1.5 minutes. Yeah, if you look at this video, there is a magnets which are kept here. You can see there is a south pole and north pole. There is another magnet which is again south and north pole. There is a magnetic field here. Are you observing these lines here shows there is a magnetic field coming from north pole to the south pole. So in this magnetic field, we are placing the conductor which is carrying the current. Now you can see that what is happening in this. So you have a conductor here, and you are allowing the current to flow in this conductor. You can see electrons start flowing from negative terminal of battery via this wire, and it flows to the conductor. In our case, we have chosen semiconductor, p-type semiconductor, but here it's a typical conductor, and you can see electrons are moving via the conductor, and the electrons will be flowing here within the conductor under the influence of this magnetic field. And what this magnetic field causes, or what is an impact of this magnetic field on the electrons? You can see that electrons started bending, and they start moving in another wire which is placed here. So this is a voltage also will get induced in other part of the conductor, okay, because of the magnetic field which deviated the electron movement in this conductor because of the magnetic field. So due to the magnetic field, a current voltage will get induced in other phase of the conductor. Okay, so that allows the current to flow in other part of the conductor as well. So let's continue this. You can see. Okay, so I hope you understood this. Okay, the Hall effect phenomenon. So what it tells you is, uh, when the current carrying conductor we have placed in a magnetic field. Okay, so in such cases, what happens, the electrons get deflected, and it will induce voltage in other part of the conductor. Now let us look at this diagram here. Okay, you can see here, as we said already, we have not shown any potential, here for the Ix. We assume that Ix is flowing here because of some potential we already set up here. So current start flowing from phase C to phase D, and you can see the holes are moving here. Okay, we have shown here holes, not the electrons. So the holes start moving. This is a p-type semiconductor bar. So holes start moving here, and they get influenced by the magnetic field what you see here. This is Bz is the magnetic field which is acting perpendicular to this current flowing Ix. So because of the magnetic field Bz, which is in positive Z direction, so this makes the electron, the holes here in this case, to get deflect, and all holes whatever coming here, not all holes, part of the holes here will appear on the face A. Are you seeing here? We are shown here with empty dots. That means the holes accumulated on face A of this conductor, and opposite will happen on the other side of the face. If holes get accumulated on face A of the conductor, definitely there should be an electron accumulation on face B of the conductor here. So holes on face A and electrons on face B, this induces potential between the faces A and B. This potential is called as Hall voltage. VAB is nothing but the Hall voltage. Okay. So this is an important phenomena what Hall has been shown to us. So we are placing a current carrying conductor in the magnetic field that induces current or the voltage, okay, between the phases A and B. Okay, and in fact, to induce the voltage, once voltage induces between A and B, it also creates an electric field which is in EY. So EY is called the Hall electric field. And other electric field what we have shown earlier is Ex is due to the applied voltage. We said that there is a voltage connected between phase C and phase D. This is applied electric voltage. So this creates field Ex is going to be in the direction of the bar or length of the bar. Okay, so this length of the bar has got electric field as Ex, and this Ex makes the holes to move from C to D. But now in the bar, because of the magnetic field influences the holes here, the holes will get deflect, and holes appear on face A and face B of this rectangular bar here. So this induces voltage between the face A and face B because of the electric field that exists here, EY. This electric field is called as Hall electric field, and voltage induced between the faces A and B is called Hall voltage. Okay, so this is overall idea about Hall effect. Now we will look into the mathematical aspects of the Hall effect. I hope in this material what you understood is there is a reference direction which will illustrate you the directions of the current, magnetic field and electric field, and we explained about Hall effect phenomenon, what happens here when we place a current carrying conductor under the magnetic field, and we told about the induction of the Hall voltage here, and we told about electric fields responsible for that. Okay, now let us go to the mathematical aspects of this Hall effect phenomenon. In the above diagram, a magnetic field is applied perpendicular to the direction in which holes drift. We have seen the hole drifting along the length of the bar. We have considered here p-type bar. The path of the holes tend to be deflected because of the holes they are flowing under the influence of a magnetic field. Due to that, the path of the holes will tend to get deflect, and holes get accumulate on the face A. Holes drift in the positive x direction due to the applied electric field. So this already we said here, when we allow the current Ix to flow, holes will get drift in the positive x direction. The direction is shown here. You can see that it is a positive x direction, which is same as this our reference direction here. Okay. Holes moves with a velocity vx. You can see that the notation small v sub x indicates velocity of the holes, okay, in the positive x direction here. Okay, I'm explaining this Hall effect phenomenon by considering the holes. You may also explain the Hall effect phenomenon by considering even electrons, and here I have chosen here the p-type semiconductor bar. You may also explain Hall effect phenomenon by considering n-type semiconductor bar and electrons as the charge carriers. So here our assumption is we consider p-type semiconductor bar and holes are the majority charge carriers in this. So we are considering here hole moment to explain the Hall effect phenomenon here. So now we will use vector notation to calculate the total force acting on the single hole because of the electric field and the magnetic field. So this vector notation, will help us to calculate the total force acting on the single hole. The total force acting on single hole is given by charge times q, because it's a positive sign you can note here, since it's a charge on hole, not an electron. If you want to change this force equation for the electron, just change plus q to minus q. Okay, so and other things within the bracket we have an electric field E plus added with the velocity of the hole in our case and the magnetic field over which the hole get influenced here. So this equation is called as a Lorentz force equation here. So this is the force acting on single hole which is flowing under the influence of electric and magnetic field here. Uh, if you look at the diagram, the magnetic field is along z direction, which we denote it with the B. Current direction is positive x direction, that's the hole moment we have shown. And velocity of the holes is also going to be in the positive x direction, which we have indicated with Vx. Okay. Now the Lorentz force act, which is get applied on each hole, okay, which is a deflected hole, is nothing but F minus phi. It is holes get deflect on the face A. You can see that holes get move started deflect because of magnetic field to the negative y direction, and so that equation is given by q times Vx into Bz. The holes that are deflected towards minus y direction is equal to q times Vx. It is the vector notation. It's a cross product. So overall force is going to be in the minus y direction. So therefore F minus phi, force in the negative y direction, it is a force applied on each hole, is q times Vx into Pz. Okay. So therefore F minus phi is equal to, if you indicate this with rewrite this equation with vector notation, which is going to be q times Vx, a vector Vx in the positive x direction, and as a vector magnetic field vector which is in the positive z direction here. So this is the force acting on the hole that get deflect to the minus y direction. Look at the diagram here. So holes get deflect into the minus phi direction. The force acting on these holes is F minus phi, shown here, is equal to q times Vx into Bz. So with that I will stop at this point. In the next class we will continue with this same force equation will continue with that, and come out with the mathematical expression for the all voltage. The voltage which is established between the faces A and B, we have to derive a mathematical equation for that, and using that equation for voltage between A and B, we need to identify a proportionality constant called as Hall coefficient. So students has to remember this mathematical the equations. Reason is in examination problems will be asked based on the equations what we are going to discuss in this class. So in the upcoming class we will see more mathematical details of this Hall effect phenomenon. So today in today's class I hope you understood the Hall effect statement and the experimental setup to understand the Hall effect phenomenon, and a simulation video what we have shown that makes you clear about the Hall effect. What do we mean by Hall effect here? With that I would like to stop at this point of time, and any queries are there, I'm very much happy to take up.